So my talk is on finding case simple paths and cycles in a graph, directed edge-weighted graph. And this is joint work with my student Udit Agarwal. Okay, so finding k shortest paths from S to T. One can think of three different variants of this problem, and we are staying with a graph, a directed graph with non-negative edge weights, and you're given a pair of vertices S and T, and the goal is to find k shortest paths from S to T. And we can define three different versions of this problem, and we are going to concentrate on the last one. So the first version is, well, find the k shortest paths from S to T, which means that you find the shortest path, and then k minus 1 additional paths that are shortest, after removing the paths that were found before then, before this path. And the point is that here you're allowed to have cycles in the path. And if you do this, then if you allow this, then this problem is easy. And there's an algorithm by Epstein that works, for k paths. It's basically Dijkstra plus k. The second version of the problem is to say find the k shortest paths, but they should all have distinct edge weights. So if you have multiple shortest paths with the same weight, then they don't count. You just output one path with each weight. Now this turns out to be really hard in the sense that it's NP hard even for k equals 2. And the problem that I'll be looking at is the third one, which is intermediate in complexity. And this is a well-studied problem. Find k simple paths from S to T. So you don't allow cycles. And in fact, the paper by Epstein claims that this version, the version I'm going to look at, is in fact more common in practice than the one that he looked at. So even though this is not that well known in the theory literature, it's actually quite a common problem. And for this problem, there's an algorithm, a classical algorithm by Yen, that runs in k times O tilde of k times mn time. Again, we'll always be using m as the number of edges and n as the number of vertices. And there have been small improvements since then, but it remains in O tilde mn. And there's a reason for that, because Williams and Williams, it belongs to the class that is hard for APSP under subcubic algorithms. And so they established that if the graph is dense, so m equals n squared. Yeah?
What was the definition of k simple source paths? Why can't you just run Dijkstra k times, or what is
no, it? But if you just run, huh? Oh, the condition is that you fix S and T, and you want a sequence of k paths that are shortest from S to T. So of course, they may be multiple, but then if there's only one shortest path from S to T, then you have to generate the next path, which may have length that's longer than the shortest path. So you just keep doing that,
But they're not overstacking, right?
I'm sorry?
Overlapping.
They can overlap. Oh yeah, they can overlap. They just have to be. You can't output two identical paths. Yes. Oh, okay.
The algorithm for k equals 2 would be to find the shortest path and then delete every edge, find the shortest path in the remaining graph.
That is certainly one algorithm to do it. And in fact, okay, so that's basically been the technique in the past. Yes, the problem that you are referring to, so the problem that Russell was mentioning is, well, the way you would find the second shortest path is to find the shortest path, then find a shortest path for each edge on the path, remove the edge and find a shortest path in the graph, and then take the path of minimum weight among these paths. That, by the way, this problem is called the replacement paths problem. I'll be talking about this like midway through my talk, but thank you for pointing that out, okay? And in fact, all of the previous methods, in fact, work that way. And by the way, I'm looking at the all pairs version of this problem, and I'm going to present a different method of finding it. So that's, in fact, the algorithmic. So is that clear now? So that's, yeah. So, and that turns out to be a lot more challenging than just finding, for the k shortest paths without requiring them to be simple, you can essentially do something like Dijkstra. But I mean, you have to do a little bit more, and Epstein has that, yeah. The first one will, you can always get the first path to be simple, but successive shortest paths, you're requiring them to be simple. I mean, okay, so let me take, good. So you have S and T. So this is the shortest path. And it may turn out that the shortest way to get to S to T the second time is to take 2 edges in here, then go back to S, and then come in this way. This is shorter than any other path that goes to T without having a cycle. Okay? So the first version of the problem, the easy version of the problem, doesn't care if cycles are formed, so it could generate paths like this.
So once you have a path, you can use these edges for free.
Yes, well, by free meaning that each successive path, the only requirement for your kth path is that it be shortest such that it doesn't exactly coincide with any of the paths generated earlier. Is that clear? Yeah.
Yeah, it's still unclear. Why would you even go out and go back? Why don't you just start and go directly to T?
Well, it may turn out, depending on the edge weights, you know. So it may turn out that all paths.
0 weight.
No, but you have no control over the weights. You're just given an arbitrary graph, and here is a shortest path from S to T. And if you look at the third version of the problem and consider maybe there's just one other path that goes from S to T without actually creating a cycle, and that has a very expensive edge on it, while there are plenty of paths that, okay, there are 2 of them, and then the third one goes like this and then goes like this, and that's a lot more cheaper than going out like this. Yeah.
Maybe the example can be doesn't go back to the S.
Yeah, it doesn't have to go back to S. It can go to something else. Sorry, it doesn't have to go back to S. I went to this because I have an example later on where I do go back to S. But in general, any cycle is not allowed. So you may have another, yes, so you could have something like this, and then just goes in like this, and then goes like that, and K can be arbitrary. So if you allow paths like this, then you can roughly call it Dijkstra-like techniques can allow you to generate successive paths very efficiently. While if you insist that each successive path is simple, the best known algorithm is tilde mn for constant k, and Williams and Williams have even shown that for dense graphs, it's equivalent to APSP. So it is a hard problem. And of course, for k equals 1, all 3 problems are asking for exactly the same thing, shortest path, and there always is a shortest path that's simple. So the problem that we are looking at, and we are looking at a collection of problems related to finding k-simple shortest paths and k-simple shortest cycles in a graph. The prior work, as I said, there's been quite a bit of work on k-simple shortest paths from S to T, and I'm going to be using acronyms KSISP instead of K. If it was just shortest paths, it will be SP, simple shortest paths, KSISP. And yen, and then some refinements to, within the O tilde by Gottlieb and Lowenstein, and Roditi and Zwick, more a different method. And then there is, I'm also going to look at k-simple shortest cycles. And for shortest cycles, the only prior work that we are aware of is just enumerating k-simple cycles in the overall graph, and in no particular order. You're not asking for non-decreasing order of weight or length. And this is, again, a classical problem, just like the KSISP. In the 70s, there was a lot of work in this problem, and the first polynomial time algorithm was given by Tajan in 73, and that was then improved to linear time by Johnson in 75, so kind of solved, but only in no particular order. So the variants that we study are the following. So, okay, we consider the SISP problem for all pairs. And I should mention that, I'll talk in the next slide. We don't have a full answer, but we do have some interesting improvements. And our method is interesting. It's quite different from prior methods. And then we go to the cycles version, and we consider both variants. Find the k-simple shortest cycles through a specified vertex that corresponds to KSISP, which is k-simple shortest paths from a given vertex to a given vertex. And the overall graph version is what we call K all vertices simple cycles. So for every vertex in the graph, find the k shortest simple cycles. Okay, so we consider those two versions. And then corresponding to enumeration, we have two more problems we study, which is enumerate the k simple shortest cycles, k all simple cycles, and the k simple shortest paths, k all simple paths. Okay. And so what are our main contributions? Of course, we did a systematic study of all of these different variants, but we also found new algorithms to address this property for paths through a technique we call path extensions. And with this technique, we solve two AP-SISP, that is SISP for all paths, in the same O tilde time as for a single pair. So for a single pair, it was O tilde KMN, so it'll be O tilde MN for 2 AP-SISP, and we had the hardness result from Williams and Williams, and we match that same result for the all pairs version, for all theta of n squared versions, and with this new technique that we call path extensions. And the same technique gives an improved algorithm for 3 AP-SISP, but it's a factor of n slower, but that's still better than what's the best known, which is basically running the SISP algorithm n squared times. So that's like mn, O tilde mn cubed. Unfortunately, our current algorithm doesn't scale to larger k, and that's an interesting open question. Then we use path extensions in a different way to come up with a very efficient algorithm for enumeration of simple shortest paths. So we solve k all SISP, that is generating simple paths in the graph in non-decreasing order of weight, where we spend O of m time for the first path, and that's inevitable because the first the shortest path in the graph is just an edge of minimum weight. And clearly you need to spend m time to find the edge of minimum weight. But thereafter, we just spend O tilde of j comma n time for the jth path. So essentially, if k is a constant, then each additional path is found in O of log n time. So it's very efficient. And it uses path extensions, but a different path extension method from what we used for the first problem. So those are our algorithmic, and those are our non-trivial algorithms. And then we give several reductions to obtain O tilde mn time algorithms for the remaining problems. So we considered 6 problems, of which for one, SISP, KSISP, there were already algorithms that were O tilde. And there were 2 more that were addressed by our algorithms in here. So that leaves 3 other problems, the cycles problem for all 3 versions. And we give for KSISC, so simple shortest cycles, and K all, generating all simple cycles in non-decreasing order of weight, we give O tilde mn time. So this problem is where there was prior work for the case when you didn't care about the ordering. You just wanted to generate simple cycles where you could do in linear time. But here we spend O tilde mn time, but we still have a reasonably efficient algorithm. And similar to all pairs simple shortest paths, for all vertices simple cycles, for 2 ABSISC, we have an efficient algorithm. It degrades slightly, not as bad as what we have up here. At least it becomes super mn for k greater than 2. And finally, relevant to this workshop, we show hardness results. And our hardness results, because we're mainly interested in sparse graphs, our hardness results are with respect to finding a minimum weight cycle in a sparse graph. Now, for dense graphs, this is known to be equivalent to APSP, so n cubed. But for sparse graphs, we can solve it in O of mn time. And, it's a very well-known problem. I mean, and people have certainly been trying to get better than O of mn for it. So we showed reductions from minimum weight cycle for all our problems, except, of course, for K all SISP, for which we actually have a very efficient algorithm. And the reductions we use, we call them MN reductions because, it's going to preserve the number of vertices and the number of edges in the graph. Okay, so the hardness class, just to reiterate, so the APSP hardness class is very, well known, and it's like a major theme of this workshop by Williams and Williams. But the problem is that if you're mainly interested in sparse graphs, which is often the case, it does not distinguish between dense and sparse graphs. So we just consider reductions that preserve sparsity, starting with min-weight cycle. And so let's call that sparse min-weight cycle hardness with respect to sub-MN algorithm. So if you could get a sub-MN algorithm for any of our problems, you would get sub-MN for min-weight cycle, which has been open for a long time. And I should also mention that there are other ways of approaching n-cubed from sparsity to dense graphs. And for example, for min-weight triangle, there's a very nice algorithm I should have mentioned by Itai and Roddy, which does it in O of m to the 3/2 time. So that again becomes n-cubed for dense graphs, and it's faster than Mn. But it's not quite as big a class. Mn, there are lots of problems that have O tilde, graph problems that have O tilde Mn running time for sparse graphs. So anyway, so that's not the class that's relevant for our problems. Mn is the one that's relevant for our problems. Okay, this is maybe I'll just hit the highlights here. So this is all of our results. And so for cycles, at least for cycles in non-decreasing order of weight, there's nothing known before, except as I said, for K all SISC, if you didn't care about the ordering, there's a very efficient algorithm, linear time per cycle. So our new algorithmic result, which I think is kind of the most non-trivial part of our contribution. Actually, for just the case of 2-APSISP, you can actually use something called distance sensitivity oracles that I'll define a little later in the talk, and I'll use DSO for short for that. And using them, you can do it in O of n, O tilde n cubed, so it's fine for dense graphs, but again, we want efficiency for sparse graphs, and we get O tilde Mn, and with a new method for this. And bootstrapping on that method, we get Mn squared for 3-APSISP, and that's again a factor of an improvement over previous results. And there is a lower bound here. Trivially, both of these problems are at least as hard as APSP, because they include, the output includes the APSP solution. So I didn't put that in there. And then when it comes to 2-SISP, so this is the lower bound that Williams and Williams gave for 2-SISP for under n-cubed reductions. And they used a reduction from min-weight triangle, but I mean, we can also, that reduction in fact works for sparse graphs. So we do have that min-weight triangle reduces to 2-SISP, but as I pointed out, min-weight triangle actually has an m to the 3/2 algorithm. So we give a different reduction from min-weight cycle to 2-SISP. And KSISP is the same. And so these are all new results. So we show that KSISP is equivalent to KSISC. So all the results for KSISC translate to KSISP, both lower bounds and algorithms. And all of the remaining problems, except of course the last row, which is for our efficient result, they run in O tilde Mn time. For here again, this is the all vertices version, so it's a little analogous to APSISP. So the 2 for k equals 2, it's a little faster. It's O tilde Mn, but when you go k greater than 2, right now we can only get kmn squared, but we can stay at kmn squared. We don't have to grow further. So and then for all SISC, we have, I guess, tight bounds relative to our hardness assumption. So we show that it reduces to 2 all SISC, and we can, in fact, generate each successive path in O tilde Mn time. Okay, so I won't talk, I mean, these algorithms, I'll talk about some of the reductions. For the algorithms in here, I mean, they require a little bit of work, but they're not, they're fairly straightforward. So I will concentrate on some of our reductions and then talk about our upper bound, our algorithms with the novel technique for APSISP. Okay, so Mn reductions, I mean, these are fairly strong reductions, and they work for our class of problems. We could have defined weaker reductions and still got the desired result that, improvements below Mn would imply improvements for a min-weight cycle. But we consider reductions where we say if you have two graph problems P and Q, an Mn reduction from P to Q, means that given an input to P with m edges and n vertices, we can transform in linear time, m plus 1 time, this input into a graph G prime, which, if we solve with an algorithm for Q, will in turn return a solution for P in O of m plus n time. So a very strong reduction. We can work with this definition for all of our reductions. And our main reductions, the ones that I will show you, is min-weight cycle reduces to 2SISP. Of course, this is trivial, from 2 to k. And also that KSISP is equivalent to KSISC. And of course, the remaining hardness results are pretty much trivial, because it turns out the left turns out to be a special case of the right. And also, there are some prior known results. For instance, I think it's folklore that min-weight cycle reduces to APSP. And it was shown by Gottlieb and Lowenstein that 2SISP reduces to APSP plus O of n squared processing. So there is this reduction, and in fact, you can, yeah. And then also, Brodetti and Zwick showed that KSISP reduces to K calls to 2SISP. Okay, we won't be using any of these, but just to point out reductions that are known. Okay, so showing the equivalence is fairly simple. So we'll just do it in both directions. So KSISP reduces to KSISC. We just add a new vertex U prime to the graph and put 0 weight edges from U prime to S and T to U prime. And then we see that the kth simple shortest cycle in this updated graph G prime through U prime is precisely the kth simple ST path from S to T. Okay. And the reverse, KSISC, reduced to KSISP, it was slightly different reduction. We have to go from cycle to path. So the goal is to compute K simple shortest cycles through V, so a given vertex V and G. So we split V into VI and VO. So all incoming edges to V are made incoming to VI. All outgoing edges from V become outgoing from VO. And then we can observe that a simple cycle through V in G is transformed into a simple path from VO to VI in G prime with the same weight. So we have the reverse reduction. KSISC reduces to KSISP. So the two problems are equivalent. Okay, so for min-weight cycle reduces to 2SISP, we use this generic transformation where to convert from G to G prime, where for every vertex V, we split it into VI and VO as we did for the SISC reduction, but we actually put an edge from VI to VO of weight 0. And then all incoming edges become incoming to VI, and all outgoing edges from V become outgoing from VO. And we do this for every vertex, so the incoming edges, their other endpoint is coming out of the O vertex for that vertex. So for C, it's from CO, and the outgoing edges go to the I vertex, E sub I. So we do this, and this is the graph G prime that we will, so and you can see that because we put weight 0, a simple cycle through vertex, any given vertex V in G is transformed to a simple path from VO to VI in G prime with the same weight. Okay. Now we need to add a few more gadgets in order to complete the transformation, and I'll illustrate that with an example here. So this is our reduction. So in blue is our graph G prime, and I've drawn it for 3 vertices, so n equals 3 here. So you have, and they're numbered, vertices are numbered 1, 2, 3, and you have the edge, 0 weight edge from the I vertex to the O vertex. Then we have a path, and that's the path in here on n plus 1 vertices, all with 0 weight edges. So that's P0 to P3 because n equals 3. And now we are going to connect up this path to the vertices in G prime. So if we consider the jth vertex in here, Ji to Jo, there will be an incoming edge to Jo from Pi minus 1. So this is 2O, so it comes from P1. And there will be an outgoing edge from Ji to Pi. So those are the green edges. And now we assign weights, and we're going to assign fairly large weights. First, let little w be the maximum edge weight in G. and we're going to set capital W to be n times little w. And the point of this is to observe about capital W is that capital W is greater than the weight of any simple shortest path in G prime, because the maximum weight on an edge is little w, and any simple path contains at most n minus 1 edges. Okay, so then we observed that. So the shortest path from S so we are going to consider the second simple shortest path problem from P0 to P3. To SISP from P0 to P3. The shortest path is, of course, the black path because it's of weight 0. And any other path has to take a red edge and a green edge, because those are the only edges going out of the path, and they're going to have very large weight. So the second shortest path will take one of these edges out and then traverse through the graph to get to the some I vertex, and then come back to the path and then continue to the end. And we make another simple observation, which is that it would never be, the second simple shortest path will never, if it starts out of Pj, it would never go to a vertex at Pj plus 2 or greater. And of course, clearly it wouldn't go back to a vertex before Pj, because that would create a cycle. That is, the path will have to start from Pj minus 1, that's how we have it here, and then take a path through the graph and then come back to Pj. And that's because if you sum up the weights of the corresponding red edge and the green edge, so it's n minus j plus 1 w, if you went directly to the next vertex, 2 plus jw, so that gives you n plus 1 times w. If you went to the next, took the green edge to the vertex next to the vertex from which you started out. And if you went to any vertex, green edge to a vertex beyond the next vertex, you'll add at least one more capital W, and that would never be useful unless the graph has no cycle at all or something, because any path through the graph has weight less than W. So the second simple shortest path starts from some Pj minus 1, goes in here, takes a path to the corresponding Ji and comes back. And of course, for it to be shortest, it has to take the shortest simple path in G from that Jo to that Ji, and that would be the second shortest simple cycle in the original graph G, which is what we needed to show. Okay, so, and this is a linear sized reduction and doable in linear time. I mean, this graph has O of m edges and O of n vertices, and so this is our mn reduction. Okay. So those are the only two reductions I wanted to show. I just wanted to conclude this part of the talk to just point out that, O tilde mn, just for the type of problems we've been considering, is quite rich. And also there are lots of refinements within this class. So if you look at unweighted, we have exactly mn for min-weight cycle and unweighted APSP, both undirected and directed. Next, you come to weighted. And then for the undirected case, we have an almost mn time algorithm, mn log alpha mn, for undirected minimum weight cycle and undirected weighted APSP. Now if you come to directed, then we have many of the problems we considered here, and also directed APSP with mn plus n squared log n. And then the next class is mn plus n squared log n, which is our algorithm for 2 APSISP, for 2 AV. Several of our algorithms here have this type of bound. And then DSO, which I'm going to define very soon, this is the distance sensitivity oracles. They have an additional log factor higher, but they're still O tilde mn. Now the remaining problems we considered have still polynomial time, but larger than little omega of mn till O tilde mn. Little omega tilde of, okay. Okay. So, so the rest of the talk will cover the algorithm, which, as I said, uses path extensions that may not be detours. I will explain that, why that's interesting, and talk about the algorithmic contributions. Okay, so detours. So K, what is known, as I said previously, the only problem that has been studied is KSISP, and it's been studied a fair amount. And all of the known algorithms for KSISP, and now we are considering KSISP from X to Y, compute detours around each edge in the graph. So, what is the shortest, this is referring to what Russell asked, what is the shortest path in the graph from x to y if I remove a particular edge along the path? And you find that path for each edge along the path, and then take the minimum weight edge among this collection as the answer for 2SISP, and this can be actually extended for any k. And in fact, what they're computing in the process is what's called replacement paths. And that's, again, a problem that's been very well studied, and it works only for k equals 2. And here you want to have a table so that you can quickly answer queries of the form, what is the shortest simple path from x to y if a particular edge on the path fails? So you have a table that has such an answer for each edge along this path. And all algorithms currently for 2SISP or KSISP essentially compute replacement paths, and all replacement paths can compute what's called a detour from the shortest path. And a detour is just you take your shortest path, and then you're only allowed to create your new path by exiting the current path, and of course you could exit right at x. Find a path that avoids the path, this shortest path, and comes back at some further point, like P3 here, and then continues along the path up to y. All known algorithms for either KSISP or replacement paths have used this strategy. And in fact, so much so that there's in fact even a lower bound. Hirschberger et al. Gave a lower bound, m square root of n lower bound for both 2SISP and replacement paths in this path weight comparison model, assuming that the algorithm only examines these detours. So, why would you need to examine anything else? You can show that every replacement path has to have this form. So, assuming that this is the case, then this is a lower bound. Now, turns out that our algorithm for 2S APSISP and in general for K could generate and examine paths that are not detours. So it actually falls outside the framework of this lower bound and any of these previous methods to solve SISP. Okay, so one more slide on replacement paths. I said replacement paths are very well studied and closely related to SISP, pretty much the same for known algorithms. And so the cost is you would take an algorithm for replacement paths and spend linear time, a time proportional to the length of the path, to select the minimum weight replacement path. Now you can ask about all pairs replacement paths. Now this has been studied before quite a bit, even though all pairs k-simple shortest paths hasn't been, as far as we know, hasn't been studied before. Now the problem here is that if we try to do the same strategy as up here, we notice that the output could potentially have size n cubed, because for every pair xy, we have to have an output for every edge on the shortest path, the replacement path for it. So that's pretty large. So what has been done for replacement paths for the all pairs case is to instead construct what's called distance sensitivity oracles, and this is the DSO, a compact table of size O tilde n squared, that from which any specific, you can query that table and in constant, and with you say, what about the starting from x ending to y, but avoiding this particular edge, AB. Then this in constant time, you can query the table and get the answer to this. So this was, the first DSO was constructed by Dimitrescu et al. But the current best bound for DSO is again O tilde mn, but it has an additional logarithmic factor over the other problems. But still, it runs pretty fast. Unfortunately, to get now two SISP from this DSO takes n cubed time for the same reason that we have this n cubed, because we have to find the minimum path among all of the possible replacement paths, for all pairs. So, so for dense graphs, this is still good, but for sparse graphs, n cubed is too much. So this is where our method comes in. So what we do is we have a two-phase approach. We first compute what a collection of sets called nearly SISP, K nearly SISP sets. Now what we want to find are the exact KISP sets for every pair XY. We define this quantity K nearly SISP sets, and then we give a general algorithm, compute API, very efficient algorithm that if you have the nearly SISP sets, you can actually compute the exact answer pretty efficiently in kn squared plus n squared log n time. Okay, so I will go ahead. I'll define the Qk sets first for Q2 and then for the general K. And it's, yeah, so here's the definition of the set. Given a pair of vertices xy, Q2 xy contains a shortest path from x to y. And then the second part in Q2 is going to be the shortest path from x to y, or shortest path from x to y that avoids the first edge, xb. Okay? So for example, in this graph, let's say, the exact output we want, so assume all edges are weighted 1, so we have two paths, shortest paths, both with 3 edges. So the exact answer you want are the paths xbdy and xbcy. However, Q2 is asking for, well, you take one of these two paths, let's say it takes xbdy, the second path has to avoid the edge xb, so it will have as a second path xfgdy. Okay? Now, if it happened that the two shortest paths already started with two different edges, Q2 will be the same as the exact output we want. Okay. So the point about these, the Q2 sets, is that they can be computed pretty efficiently with DSO, because each second path for a given pair xy, this second path can be obtained with a query to DSO saying, give me the shortest path from x to y that avoids this edge on the shortest path, first edge on the shortest path. So now we can, in fact, the previous bottleneck that we had, that it took n cubed to just find, query the DSO, no longer holds. At least the Q2 sets can be found in O of n squared time plus the time for DSO. And in fact, there are even faster ways of computing this, which I won't go into, to compute the Q2 sets for k equals 2. But this is good enough. DSO is good enough. So all that remains is to come, so we can compute the first path in the Q2 sets with a single APSP algorithm, and the second path using DSOs, constant number of queries for each pair. And all that remains is to compute 2 APSP from the Q2 sets, and for which I will show you this algorithm that does it with path extensions. And more generally, the Qk sets generalizes the Q2 sets. And let me just introduce this notation. So we will use P star k xy as the actual output we want, the k simple shortest paths from x to y in G. And Qk is just going to be, if the k minus 1 shortest paths in this set all start with the same edge, then the next path would be the shortest path from x to y that avoids that common edge. So there's the edge xa. If it happens that the k minus 1 shortest paths from x to y all share the same first edge, then Qk will always have the next path, the kth path, as a path that avoids the edge xa. So it's a natural generalization of the Q2 case, where we, instead of just saying the shortest path and the second shortest path, you look at the first k minus 1 paths, and only if they all share the same first edge would Qk xy potentially be different, because it has to use a different first edge. And so now with this, if suppose we have somehow computed the Qk xy sets, and we know we can do it for Q2, the task for algorithm compute APSISP is very, 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 specific. It says you already have a Qk xy, you just examine it and check, are the k minus 1 shortest paths in it all starting with the same edge xa? And if it is, then somehow determine if the kth simple shortest path also starts with edge xa, because if not, Qk already has it. It has the shortest edge outside of the edges that start with edge xa. So that looks manageable, and in fact we show that it is manageable. And for any k, I mean here this works for any k very efficiently in kn squared plus n squared log n time. So this is again the same observation. And the way we find this kth path when needed is with this following fairly simple observation, which is that if all paths in Pxy start with the same first edge xa, and that's the case that we have to kind of address, then if you now go, so this was a common first edge, and they all end at the vertex A. So if I now go to P star k of ay, so the simple shortest paths from A to y, it must consist of the right subpaths of the paths in P star xy, that is, removing edge xa. So let me just explain that. So what this is saying is, suppose we have the case, let's say k is equal to 3, and I consider the three shortest paths from, simple shortest paths from x to y, and they all start with the same first edge xa, so they look like this. The lemma is saying then it must be the case that in P star ay, well, at least the weights of the k three shortest paths from a to y must be equal to the weights in here. And I mean, they are really this. I'm just saying it that way in case you had multiple shortest paths with the same weight, and then you chose one, and this is showing something else. So this may look trivial, and maybe this addresses some questions that were asked in the beginning. And it's true, of course, for this lemma. But just observe that need not be true in general, because if I look at the three shortest paths from a to y, it might be the case that, say, this red path actually used x in order to go to y. That was the best way of, the cheapest way to go to y was to go through x. Then it's no longer the case that this lemma holds. Okay, so in general, this could happen, and this is really what complicates the algorithms for simple shortest paths as opposed to just the version where cycles are allowed. But of course, we can see that in the case of this lemma, the premise of this lemma, this cannot happen. Because if this happened, then it means that this portion of the path from x to y, it cannot use edge xa because that will create a cycle. It uses some other edge going out of x. And this portion of the path is a path from x to y, and it has weight no more than this red path. So for the purposes of our algorithm, it would already be in the Qk set. Okay? So either it's already there in the Qk set because it was in fact a path that went a different way, or it has this very structured property that all k shortest paths use xa as the first edge, and in fact the kth shortest path is just an extension by edge xa of the kth shortest path in P star ay, and that's where the path extension method comes. How much? 3 minutes? Okay. You took into account I started late, right? Yeah, okay. Yeah, so anyway, and once we have this observation, well, you still have to make sure that the algorithm is correct. There are some technical details here, but we just create, you can examine the Q sets, because it takes as input the Qk sets. By examining the Qk sets, you can see which are the problem pairs xy. And because the problem pairs xy are those for which the k-1 shortest paths all start with the same edge. And for those, you potentially may need to extend the kth shortest path from in P star ay. So you create that path, and you also, let's forget about extensions. You create that path, and what we do is we put it on a priority queue, because it may not be correct at this point, because even P star ay might be incorrect. It might be of the same form, and you may need to update it. But it turns out, so we pre-extend to x, and we place it in a priority queue. Here's the entire algorithm. It's a very simple algorithm in the sense it just uses a priority queue, and you don't even need a Dijkstra. You don't even need a Fibonacci heap. A binary heap suffices. And we can show that if you just put these paths in there and do this structured type of extraction, examination, and deciding what to do with the path, that it will correctly create the sets P star, correct sets P star, and in its running time is easily seen to be kn squared plus n squared log n, and so that gives O tilde mn for DSO, and actually we get a slightly faster algorithm. We don't need the full power of DSO. There's a very simple algorithm that will give us this mn plus n squared log n. And for k equals 3, and in general, for general k, the best method that we could come up with was to recursively use the k-1 AP SISP algorithm to compute the Qk sets. And the problem with that is we had to do that on all n vertices, so the running time increases by a factor of n with each increase in k, so it becomes worthless after k equals 4. But at k equals 3, this already gives us a faster by a theta of n, O of n factor over the best previous algorithm. And so just one comment. So this is the second algorithm that uses path extensions. This is for finding the enumerating the k shortest paths simple shortest paths in the graph. And you can see just in here that it again does path extensions, but it is it's a different type of path extension, a different criterion for doing the path extension. And for example, one difference in terms of the invariance that the two algorithms maintain is that in this algorithm, we guarantee that when we do an extension and add it to the priority queue, again it has a priority queue, it's guaranteed to be simple. In the previous algorithm, we could actually add to the priority queue a path with the cycle. It's only when we extract it that the criterion that we apply to whether or not we include it guarantees that we would never add a path with cycle. Okay, so and as I said, it's very efficient. And summary. So our main, I think the most novel contribution here is that we've come up with a new methodology for this classical problem of finding multiple simple shortest paths, where all previous methods used detours, and now we are using this path extension. And very annoyingly, our current method, it gives a dramatic improvement for 2AP SISP, basically gets the O tilde MN bound. It's also hardness O tilde MN, and pretty good for 3. It would be great if we could generalize it, and perhaps there's a different way of doing it that would give us the Qk sets. And we gave reductions, and we created the sparse min-weight cycle, which hopefully this community thinks is a good hardness class. And again, we have a different, very fast algorithm for K all SISP. And algorithmically, the questions, I think this is the question. We used a recursive method to do it. Now, the Qk sets are easier than because it relaxes what we need for the P star K sets. So you're computing something not as difficult as the P star K sets. Maybe there is some other way of constructing them that will give us a better algorithm. Now, space usage is high in all our all pairs algorithms, so it'll be nice if we can obtain space efficient versions. And finally, the hardness to sparse min-weight cycle. Now, in contrast to the n-cubed subcubic hardness results, where most of the problems were reducible to one another, here we are more like the threesome situation. We have the sparse min-weight cycle and many other problems, which reduces to many other problems. So they are all, at least as hard as sparse min-weight cycle. But so far we have not closed the reduction to get equivalence. So the one equivalence we had was between KSISP and KSISC. But in general, I think this is a very interesting class to explore. First, because in practice, graphs tend to be sparse, so it'll be good to get good results. And also, it tends to be more challenging, as I think Emmanuel Viola said, gave a talk on the first day where he talked about triangles, enumerating triangles, and the challenges that come up when you go from just the dense case to the sparse case, you have to consider, how the edges get distributed if you had to solve recursively. So there's lots of interesting, I think, questions to be addressed when trying to, refine this class of sparse min-weight cycle. Okay, and that's my talk. Questions? Yes.
You thought about hardness, trying to show hardness sort of as a function of K as well for some of these problems?
Well, okay, so, yeah, I know, but for many of these problems, for any constant K, it was, O tilde Mn. But there were a few for which it was not the case. Let me show you. It's coming pretty soon here. So the ones for which we don't have, so of course we had 2 and 3. But okay, two things. I think I can't think of a natural candidate from which to show this conditional hardness for above. But I actually think, now that I hope all of you will work on finding the Qk sets more efficiently. It's just very annoying that right now I think that perhaps KAPSISP can be brought down. I'm not convinced that there is that lower bound, but so I haven't thought about it. And there is this one, and this one is it's just n applications of SISP. So To answer your question, no, I haven't thought about it. And if you were going to think about it, it'll be interesting to see. You have to think of a suitable starting problem that has resisted, sub mn squared or something for a long time. Here, I think min-weight cycle, has certainly stood the test of time. But that's a good question. Yeah.
So I have one, and then
Yes. Yeah.
so I think because you're just using distance sensitivity oracles, your work just implies things for the dense case as well. So
Oh yeah. All of my work. Yeah.
I have a distance sensitivity oracle for the dense case where
Okay.
when the weights are small, you can do better. And so if you just apply.
Oh, for small weights. Okay, it's two comments here. One is that we have not been considering any dependence on weights. And I see. So that's interesting because, with distance sensitive oracle, with this, if you don't consider the edge weight size, we have a separate method that does it faster than distance sensitive. But if you have a faster method for distance sensitive oracle for small weights, then that would be preferable to our algorithm. Oh, that's cool. Yeah. Yeah.
So I have a-
Yeah. Yeah. So it's sub mn?
well, for dense graphs, yeah, it's.
Oh, no. For dense graphs, it would be n cubed, right? So it is sub n cubed?
for
Okay.
small.
Oh, I see. Huh.
Anyway.
Interesting. Yeah. Okay, thank you.
Thank you.